Hi, AP Physics. In this video, I'm going to be going over some capacitance conceptual problems. Here in the first one, we have 4 different capacitors with different levels of capacitance and different amounts of charge on the capacitor. And so what we want to do is we want to rank these capacitors in terms of their potential differences. So let's take a look at number 1. Right? We have a capacitance C and a charge on either side of Q. So we can write out our normal equation, right, like this, that capacitance is Q over delta V. And let's rearrange it so that it's solved for delta V, the potential difference. So it's going to be Q over C. Sweet. So this is our general equation. This is what number 1 is actually showing us. Let's take a look at number 2. Notice that the capacitance is doubled, but the charge on the capacitor is the same as number 1. So if we were solving for this, right, delta V, or the amount of delta V's, is going to be equal to Q, but it's over 2C now. So this means that actually it's going to be half, right? Compared to number 1, it's half the change in potential, the electric potential. So we know that 2 is actually going to be less potential difference than number 1. So number 1 is going to be bigger. So let's look at number 3 here. So we have a capacitance C, but a charge of 2Q. So that means it's 2Q over C. Well, that's actually going to be 2 delta V. So this is larger. So 3 is bigger. And then for number 4, we find that it's 2Q over 2C. Well, right, those 2's cancel out. We end up with just a delta V. So actually number 1 and number 4 are the same. So the order would go 3, 1, or 4. It doesn't matter. I'm going to put 1 first. And then 2 would be last, since it's got half the potential difference. So that's how we do number 1. And that explains our evidence as well. For the second problem, we have a parallel plate capacitor, and it's fully charged and is disconnected from the energy source when a dielectric is inserted between the plates. So our first image on the left over here is before the dielectric is placed in, and now we have the dielectric in place. And we want to sketch the electric field between the plates to show this effect of polarization of the dielectric. So the electric field's really going to be only between the charges that don't have something for the dielectric to hold on to. So notice that we're having much less electric field lines than before. So this is A. That's what we do for A. For B, we want to identify, is the electric field between the plates larger, smaller, or the same as it was before the dielectric was inserted? Well, clearly we have less electric field because the electric field lines there are less of. So it's actually going to be smaller. And so since the dielectric is polarized, this means that the unlike charges are going to be closer, and this is going to limit the electric field that can pass through. Since the positive and negative charge, right, these two are really nice and close together, right? Then the electric field coming from those charges are going to be stopped at that dielectric. So if the electric field has gotten smaller, what's going to happen to the potential difference? Well, we know that the potential difference is going to be equal to the electric field times the displacement. Well, since the electric field has gone down, right, E goes down, well, this means that the change in voltage is also going to go down, right? We haven't made the distance between them smaller, but we have made the electric field smaller. And then finally, what about the energy stored? Well, we have the equation for the potential energy stored is Q over 2C. And notice that the charge on either plate hasn't been made smaller by the dielectric, but the capacitance has gone up, right? This is what a dielectric does. It makes the capacitance go up by making the voltage go down. So if this is the case, then that means that since it's an inverse relationship with capacitance, then the potential energy is also going to go down. All right. Now let's find some equivalent capacitance. Let's practice that a little bit. So each capacitor is going to have a capacitance of C, and we're going to find out how many C's or what a fraction of a C it's going to be. So let's look at the first one here. So we have two capacitors in a series, right? The equivalent capacitance, right, in this case is going to be C over 2. We know this because it's going to be, right, the equivalent capacitance looks like this. It's going to be 1 over C plus 1 over C. Whoopsies. 1 over C. So if this is the case, right, we get 2C. So we flip that upside down, and we get our answer. Let's try out the second one. This time we have it in parallel, which is the exact opposite. So if this is the case, draw a line here. All right, so if this is the case, then we just add up the capacitances. So there's 2 here. So the equivalent capacitance is just going to be 2C, right? Because equivalent capacitance is just C1 plus C2. Cool. Let's clear this and make a new one. All right. The third one is just 3 capacitors in a line. Right, a little bit janky here, but got the idea. Well, it's the same thing, but in this case, right, to find the equivalent capacitance, right now we have 3, so it's going to be C over 3. What about 3 in parallel? Chunk, chunk, chunk. 3 capacitors in parallel, all with capacitance C. Well, again, we're just adding it all up together. So the equivalent capacitance is going to be 3C. All right, so we should be getting the gist between parallel and in series. Now, what if we start mixing them up a little bit? So this time, we're going to have them in parallel, but then 2 in series on each parallel. Okay, so, right, if they're in series, well, these 2 come together to make half a capacitance, and so do these, right? Same thing. And then we add them together. So if we, right, because in parallel we add the capacitances. So in this case, the equivalent capacitance is just going to be the original capacitance. So we used 4 resistors to get the effect of, 4 capacitors to get the effect of 1 capacitor. And then the last one. What about 1 here, then 2 in parallel, and then a final one in series? Well, first we should do the ones in parallel so that we can add them all up in the series. So if this is C and this is C, right, it's going to give us 2C. And then if we want the equivalent capacitance, well, that's going to be 1 over equivalent capacitance for those in series. So it's 1 over C plus 1 over C plus 1 over 2C. Whoopsies, that looks like a G there. All right. So this is half of a C, so we're going to get 2C here. And this is going to be plus, sorry, we can change this around actually. So that's 2C, but let's make that 4 over 2C. plus 1 over 2c. Sweet. Add those together. We get 5 over 2c. Which means that the equivalent capacitance is going to be 2c over 5, or 2/5 capacitance. Cool. So this last one's a little bit complicated, but notice how we started off with the ones that were together, and then we moved to the ones that were in series. Lastly, for number 4, it says, without using a mathematical formula, explain why the equivalent capacitance of any number of capacitors in series is always less than the individual capacitances, and why the equivalent capacitance of any number of capacitors in parallel is always greater. Well, if you think about it, when we put them in series, right, when we stack them on top of each other, essentially what we're doing is we are increasing the distance between the two plates. And the opposite is happening for the ones in parallel. What we're doing is we are increasing the surface area between them. This is what we are doing when we place them in series. We essentially increase the distance between the plates. And 2, we are, when we put them in parallel, when we put them side by side, we're actually, in essence, increasing the surface area of the plates. All right, this should be those conceptual problems. The next video, I'm going to go over some more ranking tasks.